This is going to be section 8.4, video number 3. And we're going to look at the third case when it comes to trig substitutions. So the third case that we're interested in is going to be the case where our expression in the denominator of our rational function is going to be the square root of x squared minus a squared. So compared to case number 1, the subtraction is going in the opposite order, variable minus constant. And then, of course, in case number 2, we had an addition sign. So 3 different scenarios. Case number 3 represents the final scenario that we'll look at today. When this occurs, we are actually going to let x equal a times the secant of theta this time. X is going to be a times the secant of theta. I'm going to go through the exact same process as I went through with the first 2 cases. If I utilize a right triangle and select an angle theta, then the secant of theta, according to this expression, would have to be x over a, where the secant ratio is the hypotenuse over the adjacent, making the length of the hypotenuse in the triangle x, and the adjacent side a. Using that information, let's write an expression for the length of the opposite side in this triangle. The Pythagorean theorem is going to dictate that I'm going to take the hypotenuse squared. I'm going to subtract the side that I know, squared, and then I'm going to square root that difference. So, let's take a look at what substitution we are going to be able to make for that square root of x squared minus a squared by first plugging in the x expression. So I'm going to have the square root of the quantity a secant squared, or a secant theta squared minus a squared. Squaring out each individual piece results in the following 2 expressions where they both have a common factor of a squared. So my next step is going to be to factor out that a squared. And what we're going to get is another version of a Pythagorean identity. So it's basically the same Pythagorean identity as we used in case number 2, it's just the opposite version. So here I'm going to let secant squared theta minus 1 become tan squared theta. And if I simplify, I again forgot to carry down my squared there. If I simplify the square root of this, it becomes a times the tangent of theta. So here's the summary of case 3. X is going to be represented by a times the secant of theta, and therefore the square root of x squared minus a squared can be represented by a times the tangent of theta. Very similar to case 2, except these are switched. So let's take a look at an example involving that case. So the example we have here is going to be finding the antiderivative, or the integral, of dx over the square root of x squared minus 81. Again, case 3 applies because of the order in which the subtraction happens underneath the square root. Once again, great idea here for you to try to do the setup. So if we have you identify what x and a are, have you figure out what dx would have to be, Also determine what substitution can be made in the denominator, and then tell me what the new substituted integral would be. So I would recommend pausing, trying to fill all that out, come back and check your answers. A should be 9. That means that x should be 9 times secant theta. The derivative of secant is secant theta tan theta. And then the substitution that we're going to make here in the denominator is going to be 9 tan theta. So our new integral, if I substitute dx and I substitute our denominator, the 9's are going to cancel, the tans are going to cancel, and so really I'm just finding the antiderivative of the secant of theta d theta. Alright. Finding its antiderivative goes back to that formula once again, which is going to be the natural log of the secant of theta plus the tangent of theta, and because it's an indefinite integral, plus c. Very last step, let's replace all of our thetas with an expression involving x. So go back to some equation that we wrote that relates x and theta. X equals 9 secant theta is probably the most obvious. If I solve that for theta, I'm going to get the inverse secant of x over 9. I apologize, I wasn't really paying attention. What I actually want to substitute is not just theta, but the secant of theta. So if we think about isolating just the secant of theta, that's going to be the expression x over 9. And you could have also gotten that by taking this entire theta and plugging it in here, and the secant and inverse secant would just cancel each other out. So either way you get it, it's fine, but we want x over 9 there. Here, we want to figure out what the tangent of theta is. So we could do something similar to what we did in the last example, where we take the inverse secant of x over 9 and we plug it in for theta, and then we draw a triangle to figure out what the tangent ratio would be for that same angle. The other option is that when we substituted, one of the substitutions that we made was for the tangent of theta itself. So we said the tangent of theta was equal to the square root of x squared minus 81. Sorry, that was 9 tangent of theta. So anyway, we can go ahead and solve that for the tangent of theta, which would be x squared minus 81 square rooted all over 9, and then plus c. A couple of different ways that you can do it. Hopefully you've got some method that makes sense in terms of figuring out these two theta expressions in terms of x. One last note to make in this section. I can do a little logarithmic property simplification where I've got a common denominator here that I can add together. And then the log property happens when you're taking the log of an argument that is a fraction. You're allowed to rewrite that as the log of the numerator minus the log of the denominator. So if I do that here, then I'll have the natural log of x plus the square root of x squared minus 81 minus the natural log of 9 plus c. What you'll probably see happen in MyMathLab is that they'll combine these like terms. If you were to calculate the natural log of 9 on your calculator, it'd be some decimal constant. And when you add one constant with another, it remains a constant. So it's not important that we quantify what that constant is, as long as we say that there is some constant being added. So what MyMathLab will probably expect is that you don't write that natural log of 9 term, and instead just write the term that has the variables in it, and then plus c. It will probably count this answer wrong. And if you wanted to send me a note about that, I could of course manually give you credit, or you could just go ahead and do this.